Yeah, good morning, everybody. I'm going to talk on gravitational lensing in the presence of a plasma. That's a subject I've been working on over the last 25 years or so, with interruptions. And I will now tell you in 30 minutes everything I learned in this 25 years. So I will restrict to ray optics. So the light propagation is described in terms of rays. And I will use a Hamiltonian formalism. So that's the first thing I will explain to you, how this Hamiltonian formalism works. Then I will speak about a variational problem for light rays in this context. So instead of using a differential equation for describing the rays, you can also use a variational principle, which is a version of Fermat's principle. And I will talk about the equation for bundles of light rays. These are the Sachs equations. So it's a generalization of the ordinary Sachs equation. So these first three sections will be on an arbitrary general relativistic spacetime. I will then specify two stationary spacetimes and the stationary plasma. And I will talk about the issue of separability of the Hamilton-Jacobi equation, which is necessary in order to write down the solutions analytically. And so in order to have complete integrability, so you need something as like a generalized Carter constant. So that's what I will talk about. And if this exists, then we can write down the photon region analytically, and we can write down the shadow analytically. And then I will further specify to the Kerr metric, and again discuss the separability issue, the issue of photon regions, of shadow, and also of the bending angle in the Kerr spacetime. So that's the program for the next 30 minutes. Let's begin with the Hamiltonian formalism. So you can write down the equation of light rays in such a medium. I should say what I mean by a plasma. When I just say plasma, I mean the simplest model of a plasma we can imagine. It is an electron-ion plasma. It is non-magnetized, so no magnetic field. And it is what the plasma people call a cold plasma. This means that the electron fluid is described as a dust, as a charged dust. The pressure is neglected. Actually, a cold plasma can be fairly hot. Yeah? So for instance, the solar corona has 1 million kelvins or something like that, that I wouldn't call cold by everyday standards, but nonetheless, a cold plasma is a very good approximation because the density is very low. Yeah? So the terminology is maybe a little bit misleading. Maybe pressure-free is a better word. Okay, so that's the kind of media I want to consider, and I claim one can write down the equation for the light rays in the usual Hamiltonian form, as we learned it in our first course on classical mechanics. And the Hamiltonian is this here. So if this term here, this omega p of x is not there, then this set of equations will just give you the light like geodesics. These are the vacuum light rays. If this omega p is non-zero, then you are in a plasma, and the omega p squared is essentially the number density of the electrons. Yeah? The four velocity of the electrons plays no role. It just drops out from the equation for the rays for this type of plasma, for the simple type of plasma. So that's the set of equations with which we are dealing. This equation h equals 0, that's what we call the dispersion relation. Yeah, the restriction on the four momenta, which four momenta of a light ray have to satisfy. So this set of equations doesn't come out of the thin air. It can be derived from Maxwell's equations. If you assume a two-fluid model for one fluid for the electron, one for the ions, then you can really derive this set of equations from Maxwell's equation. And on a curved spacetime, I'm here on an arbitrary general relativistic spacetime. On a curved spacetime, this was first done rigorously by Breuer and Ehlers in this paper in 1980. They even did it for a magnetized plasma. If you are satisfied with a non-magnetized plasma, you can find the derivation also in my book. Okay, here are again Hamilton's equation. So let's look at this part of the equations. If you write this out, you see that the tangent vector to the rays is just the momentum co-vector with an index raised. And if you insert this into the dispersion relation, you get this equation for the tangent vector, which tells you that the rays are time-like. Yeah, if omega p is non-zero, then this is negative, which means that the tangent vector is time-like. And actually, the curves are time-like geodesics. If you look a little bit closer, you will see that they are geodesics, not of the space-time metric, but of a conformally rescaled space-time metric. So the rays in a plasma form not the boundary of a light cone, they fill the entire interior of a light cone. Yeah? And this is a characteristic feature of a dispersive media, which can be made more explicit in if you use a 3+1 decomposition. So if you choose an observer field, a time-lag vector field u, and you decompose the form momentum with respect to u and a component parallel to u, this gives you a frequency omega and a component perpendicular, which you then call the wave covector. Then you see that the dispersion relation, the equation h equals 0, takes this form. And maybe this looks more familiar to some of you. So if you plot this, if you plot this, then you get this curve here, omega as a function of k. So in vacuum, you have this straight line. Omega is c times k. And in a medium, you have this, this cutoff here at the plasma frequency. So the omega cannot be smaller than the plasma frequency. This will also be seen when you calculate the phase velocity, omega divided by k. It comes out bigger than c. But this should not be a reason of worry, because the phase velocity is not the velocity of the signal. Yeah? So there's nothing suspicious about this. The group velocity, the omega by dk, is always smaller than c, and the product of the two is actually always equal to c squared. So the group velocity is just the inverse of the phase velocity. And also introduce an index of refraction, if you like. This is a ratio of the vacuum speed of light to the phase velocity in the medium. And this is given by this expression. Here you see again that the omega must be smaller than omega p. Bigger than omega p. So if you try to send a signal with omega bigger than omega p into such a plasma, then it just gets stuck. It cannot propagate. So propagation is possible only if omega is bigger than omega p. On the other hand, if omega is very much bigger than omega p, then you can neglect this term here, and you are practically in vacuum. So the relevant case, the interesting case, is that the omega is bigger than omega p, but not very much bigger than omega p. Here are a few numbers. So for the solar corona, the omega p is something like 100 megahertz. For the ionosphere, it is 10 megahertz. So 10 megahertz, that corresponds to 300 meters approximately wavelength. If you try to send a signal with a wavelength which is bigger than 300 meters approximately, then the signal will just bounce back. Yeah, it will not enter into our atmosphere. So if there is a star or some other astrophysical source which sends rays at a frequency which is smaller than this here, it cannot be seen on the ground. Yeah, it's just reflected from the outer surface of the ionosphere. So in the interstellar space, the density is even lower, and in the intergalactic space, it's even lower than that. So you see all these frequencies are far in the radio regime. Yeah? And I told you if omega is much bigger than omega p, you can forget about the plasma. So this means that for optical observations, the plasma practically plays no role. Well, I'm particularly interested in a plasma which surrounds a black hole, where the density may be bigger than this, but not by many orders of magnitude. Maybe by 2, maybe by 3 orders of magnitude, but not more than that. So you're still not in the optical regime. You're still in the radio. So this is something you should keep in mind. All I'm going to say is relevant only in the radio. Okay, now let's, so this is a set of equations which we have to deal with, a set of equations for the rays. If you don't want to work with this differential equation, this Hamilton's equation in the form of differential equations, you can also use a variational principle. This is often recommendable. And for the sake of comparison, let me first talk about Fermat's principle for vacuum light rays. So this is a story which has a long history. So it began with Hermann Weyl. He formulated the Fermat principle for light rays, for vacuum light rays, on an on a static space-time, Then Levi-Civita generalized this to stationary space-times. Temple considered space-times without symmetry, but he worked in a certain local coordinate system which didn't allow crossings of light rays. So he excluded caustics. So this was a local version of Fermat's principle, but on spacetimes without any symmetry. Hofner was the first who formulated a completely general version of Fermat's principle on an arbitrary spacetime and without any restriction to locality or anything else. But he didn't prove that the solution to the variational principle are really equivalent to the light-like geodesic equation. He proved only one direction. the direction that the geodesics were actually solutions of the variational principle, but it didn't prove the converse. So the converse was proven by myself in this paper, which is the harder part actually. Yeah, so the other direction is fairly obvious. Okay, so how does this work? This principle, as it was formulated by Kovner, you fix a point in an arbitrary space-time, and you fix a time-like curve. And this curve is supposed to come with a parametrization. Maybe proper time, but any other parametrization would also do. And then you shoot out trial paths. Trial paths, these are curves which move at the speed of light. So so they are light-like curves, but of course not light-like geodesics, not necessarily light-like geodesics, all light-like curves, which start at P and terminate at gamma. And the task is to find out which of these curves are actually geodesics, which are really light rays in vacuum. And the answer is you have to look at the arrival time. That's a parameter which is given on the world line gamma. So you assign the arrival time to each of these curves, and then you consider those curves which make the arrival time stationary. Actually, it can never be a maximum. It's either a minimum or a saddle. And the solution, that's what you can prove, and that's the theorem which tells you that Fermat's principle works in this form. The theorem is that the curves which make this functional stationary, this arrival time functional stationary, are indeed the light-like geodesics. This has interesting applications to lensing. In lensing, you would consider the time reverse situation. So you would turn this diagram upside down. You have an observer here, and you have a light source here, and then you find all light rays which connect the light source with the observation event. So you find you find out how many images of this object are actually seen in the sky. Okay, that's for vacuum. Now, what do I have to do in the plasma? There's a new aspect. The plasma is a dispersive medium, so I have to say something about the frequency. I have to fix the frequency in a certain way. And I do this in the following way. Same setting. I have a point here, a time-like curve there. And I have the tangent vector to this curve, in particular at this point here where a trial curve arrives. Then I can parallel transport this vector, which gives me a vector field W along the trial path. And with respect to this time-like vector W, I can assign a frequency to each point of this light ray. And now my trial paths are curves which go at the speed of light, which means there must be a light ray tangent to each of these trial curves at each point. But in addition, also the redshift law has to hold. Yeah? The redshift law, which is part of Hamilton's equation. So the component of the equation pi dot is dh by dxi. The projection onto this vector W. This gives you a frequency, actually a differential equation for the frequency, and this has to be satisfied. So if you fix also the frequency in this way, then you can prove that the solutions are indeed the solutions of the variational principle, which makes the arrival time stationary, that these are exactly the solutions of Hamilton's equation. And this was proven in this paper in 2001. It is parallel transported. That's how I construct it, yeah. So if you have this curve gamma with a parametrization, then this vector field W is really constructed. It is not, there's no choice. Okay, so much for the variational principle. Let me talk about the equation for bundles. If you don't want to consider just one ray, if you want to consider an entire bundle of light rays, then you have in the ordinary formalism the famous Sachs equations. They were mentioned by Nessehe, and they certainly also played a role in the background of what Nikolai was talking about. So in the ordinary formalism, you have a light-like geodesic, and then you consider neighboring, infinitesimally neighboring light-like geodesics. Here we have a light ray in the medium, which is a time-like curve. So K is a time-like vector now, the tangent vector to the ray. And then you consider two vector fields y1 and y2 along this central ray, and they span something which you may call an infinitesimally small bundle. And these vector fields y have to satisfy the condition that they are perpendicular to k, which in our case, where k is time-like, means that they are space-like. Yeah? And then you consider the change of the y's along the ray. This gives you the deformation of the bundle. Yeah? And in order to formalize this, you introduce what is called a Sachs basis. Well, here we are dealing with generalized Sachs basis. So these are, two vector fields E1 and E2, which are orthogonal to each other, orthonormal to each other. They are perpendicular to K, which again means that they are space-like, and they are parallel transported, but not with respect to the Levi-Civita connection of the space-time metric, but of this conformally rescaled metric, which with respect to which the light rays are geodesics. Yeah? So this is the setting. Now you have an auto-complement of the K, which is space-like and three-dimensional. You have only two vectors which span them. So if you expand the Y with respect to the spaces, you will in general have a rest, yeah, which is not a multiple of E1 or E2, but still perpendicular to K. So this is this term here. But it will drop out if you consider this transformation matrix D and write down a differential equation for this. That's what you usually do, also in vacuum. You decompose this expression now into an antisymmetric part, into a shear part, and a pure trace. And you define the optical scalars. So these are four real numbers. You make them into two complex numbers. And you get differential equations for the rho and for the sigma. So these are our generalized Sachs equations. And here's how they look like. The red equations are the ones which you are familiar with from vacuum. Yeah? But here you have a couple of additional terms. You have here this term which involves the Weil tensor, the conformal curvature tensor. In vacuum, where the K is light-like, these two terms are zero. But in the medium, they are not. Yeah? And then you have terms which really come with the plasma frequency, or with derivatives of the plasma frequency. So this set of equations was derived by a master's student, which I supervised together with Dominique Schwarz. Her name is Karin Schulte-Kops, and the results are published in this paper. And because Dominique is a cosmologist, he was particularly interested in applications to cosmology. So one thing which we worked out was a generalized Etherington law, or which is also known as the reciprocity law. I guess most of you are familiar with this. It gives you a relation between the luminosity distance and the area distance. And in the standard formalism, where you have vacuum light rays, light like geodesics, they are just related by a factor 1 plus z squared, yeah, by two redshift factors. In a medium, you have to distinguish the redshift factor with respect to the frequency and the redshift factor with respect to the wavelength. These are different. In vacuum, they are the same. Yeah? But here you see that one of the redshift factors is actually related to the frequency, and the other one is to the wavelength. Now the question is, can this be observed? Where, as I told you, the intergalactic medium is the density is very, very low. And actually, with what we can observe here on Earth, where the ionosphere prevents us from seeing very, very long wavelengths signals, actually, we found out that there is no hope to observe this. But if we have instruments which allow us to see very, very long wavelengths radiation, and there are programs to construct something, there was a proposal for something which was called OLFAR, not to be confused with LOFAR. Yeah, OLFAR, so they interchanged the two first letters. This was a system of radio telescopes in an orbit around the moon. That was the idea. And with these instruments, actually, it might be, which was the proposal, which at least until now was not realized. With this instrument, it might be possible to make this accessible to observations. Okay, now, so everything I said until now was for arbitrary spacetimes, no symmetry. I think I'm losing this thing here. Oops. Now let's specify to stationary spacetime. Actually, I do not want just to write down Hamilton's equation. I want to solve it. And in order to solve it, to write down solutions, in the first step, to reduce it to first order, I need constants of motion. Yeah? Otherwise, I cannot write down the solution explicitly. And if I am on a stationary and axisymmetric spacetime, then I assume that the metric of this form is of this form. So the only cross term is a dt phi term. You can prove that this is a necessary condition in order to have separability. Yeah? So if this condition is not satisfied, if you cannot put the metric into this form, you cannot, you have no chance for separability. It's not the general form of a stationary and axisymmetric metric. Yeah? It's not always possible to kill all other cross terms. But I have to assume that we can do this. Then I write down the Hamiltonian, this here, with a plasma density which is allowed to depend on r and theta, so it should share the symmetry of the space-time. I write down the Hamilton-Jacobi equation, and I want to have it to separate. So this would give me another constant of motion in addition to the p phi, the momentum associated with the angle phi, the constant of motion associated with the time-like symmetry, which I denote omega naught because it has a dimension of a frequency. And then the rest should separate into a function of r only and a function of theta only. And if this is true, then it gives me a Carter constant. So I can rearrange Hamilton's equation in a way that on one side I have only functions of r, on the other side only functions of theta. And this means it must be a constant. That's what we call the Carter constant, or generalized Carter constant. So the question is, what is the condition on the space-time, which has coefficients a, b, c, d, and p, and on the plasma density for the separability to hold? And the answer was given in this paper by Barbara Betzlikova, Gigi Bichak, and myself. And there are two conditions on the metric, and there's one condition on the plasma density. So the first two conditions are only involving the the metric coefficients. So B and D are two of the metric coefficients. That's the GRR and the G theta theta, and they must be of this form. So there must be a function of theta only and a function of r only, quotient of these. Then we can define this function f here, which will play a major role in the following. And with the help of this function, we can write down this expression, which involves the other metric coefficients, a, c, and p. And they must also separate in the form of a sum of r only, function of r only, and a function of theta only. If this is satisfied, then our metric is good. If it is not satisfied, yeah? Yeah, sorry. Here's the other metric coefficient. So A, B, C, D, and P. That's the terminology, yeah? So, yeah, Barbara introduced this terminology. It's a little bit non-orthodox, but so we are using this here. So these are conditions only on the metric. And if they are not satisfied, you can stop any attempt. Yeah, then it cannot work, whatever you do with the plasma frequency. But the third condition, which must also be satisfied, is that the plasma frequency must be decomposed in this decomposable in this way, function of r only, function of theta only. And if all this is satisfied, then actually you can write down a first order equation. So you have enough constants of motion for what is called complete integrability. And I already said that separability has to hold for the vacuum light rays if it should hold for any plasma density. Yeah? So in the beginning, we had some hopes that maybe if you are in a space-time where the vacuum equation do not separate, that you can introduce a funny plasma density, so then you get separability, but this doesn't work. Yeah, it is impossible. And the second remark is that you know from the ordinary formalism that the Carter constant is associated on the Kerr spacetime with a Killing tensor of second rank. And actually there's an analog or generalization to the situation we have here. We are considering only light rays. That's why we can expect only a conformal Killing tensor, yeah? A Killing tensor of a conformally rescaled metric. And you see the constants of motion, the Carter constant, is not just constructed from this Killing tensor. There's also a contribution from the plasma density. Yeah? So this is, but you must have this second rank conformal Killing tensor, otherwise separability cannot work. Okay, now if these conditions are satisfied, you can write down the photon region and the shadow analytically. Yeah, you can really determine them. I don't expect you to learn all these formulas by heart. I've just written them down to show you that you can write down everything analytically. Yeah, you have these constants of motion, p phi, the Carter constant, and the omega naught, which is flying around inside this expression. That's a PT essentially. Yeah, the momentum associated with a time symmetry. And then the photon region, the region where you have light rays which stay on a sphere. Yeah, spherical light rays. That's what we call the photon region. Well, we call this the photon region since more than 20 years. Now some people like Alex Lubsaska start calling it the photon shell, yeah, just to confuse the community. But I'm used to call it the photon region since many years, and I stick to this terminology. So this is the condition for the photon region. So it's given by an inequality, so it's really a region in space-time. Yeah, it's not a surface or a hypersurface, it's really a region. And with the help of this, you can then construct a shadow. You have to introduce a certain tetrad with respect to which you, write down the tangent vector to your light rays. So you introduce two angles in the sky, theta and psi, by this construction. So with the help of this, you can decompose the tangent vector to a light ray in the usual way, so that they are represented by these celestial coordinates, the azimuthal coordinate phi and the declination angle theta. And you can equate this to this form of the tangent vector. It must be the same thing. And this tells you where in the sky you see a particular light ray. And here's the answer. So you can write down the formula for the boundary of curve of the shadow fully analytically. Yeah? So that's the equation for the theta, for the declination angle, and that's for the azimuthal angle. And what enters are the constants of motion. Yeah, the Carter constant, the PT, and the P phi. And I show you pictures. We did a couple of examples in the paper with Barbara and Jiří. But before I do this in the plasma, I want to remind you how it looks in vacuum in Kerr, just to have a comparison. So here's a photon region. Alex showed a similar picture. This is from my living review. Here's this picture. So it has this, the cross section has this crescent-like shape. And so to each point of this region, you have a light ray, in this case a light like geodesic, which stays on a sphere. Yeah? But as Alex pointed out, the motion is actually quite complicated. It's not planar, by far not planar. Yeah? So in particular, the phi coordinate can be fairly complicated. Yeah? It may even turn back. Yeah? Inside the ergo region, it might process first in this direction and then it goes back. This is possible for some light rays. But the theta motion is quite regular. It just oscillates between the boundary points of this region, and the R is a constant. Yeah? So it's a spherical light ray. And now what is the shadow? The shadow is, the boundary curve of the shadow is made up of all light rays which asymptotically spiral towards these. They're all unstable in the Kerr spacetime. All these things are unstable, so other light rays can spiral towards this, and this gives you this, these well-known pictures for the shadow in the Kerr spacetime. So here, that's for an observer. It's an extremal black hole now. For an observer in the equatorial plane, and that's for a polar observer, and in between the picture becomes more and more symmetric. So if you watch from the top or from the bottom, you cannot see the spin. It's not reflected in the shape of the same. So that's for the sake of comparison. So in a plasma, we considered in this paper with Barbara and Jiří a wormhole. That's a particular wormhole of the Theo class, the class which was introduced by Theo in this paper here. And we consider this type of plasma density. And so now we can ask ourselves, what is the photon region in this? What is the photon region in this situation? So here is first in vacuum. So if you have no plasma, then you get this. So this is the neck of the wormhole. Yeah, so you have two copies of this region outside of this black disk, and you have to glue them together. This gives you the entire wormhole. Yeah? And you see for the vacuum rays, you have a photon region which is extending up to the neck. So you have on both sides of the neck, you have a photon region. And if you now crank up the plasma density, here we choose this particular form of the FR, the 1/√R dependence. Then it becomes detached from the neck. So you have now two tori. On each side of the wormhole neck, you have a toroidal photon region. So it's quite different from what we are used to from Kerr. In particular, it's always detached from the axis. Yeah? In the Kerr case, it extends down to the axis for a Kerr black hole. Here it is detached from the axis. And the shadow looks like that. So this is again in a plasma. So you see here you have again this offset, which is related to the spin, of course. And the shape is not very much similar from what you know from Kerr. And we did a couple of other examples of this kind. So this was stationary spacetimes different from Kerr. Now let me talk a little bit more in the last part about Kerr spacetime, but now with a plasma. Yeah, I've shown you the photon region and the shadow in vacuum. Now let's talk about the plasma case. This was discussed in two papers together with Oleg, which appeared in PRD, with 7 years difference. And so we had to work out some of the things with some with some problems. It took us some time to understand a couple of things properly. And here's our good old friend, the Kerr metric. And we assume we have a plasma density which shares the symmetry, so it depends only on r and theta. Then we have these constants of motion, and we want to have separability, so the plasma density must be of this form. If it is not of this form, you cannot solve anything analytically. We can, of course, do ray tracing, that's always possible, but you cannot write down anything analytically. And so we discussed the photon region and the shadow for various plasma densities. I show you here a picture for the constant plasma density. You might say that's not realistic. It's absolutely true. But yeah, it's conceptually interesting because it gives some features where you learn something about the formalism. So the first thing which you see, so this is the photon region. So this orange orange region here, this is the region where you have unstable spherical light rays. Yeah, so this is analogous to this thing in which I've shown you in the Kerr metric before and in the wormhole metric. But here you have also stable circular, spherical, not circular, sorry, spherical light rays. This is this green dashed region. And you have a region where the light rays cannot enter. Yeah? This is this cross-hatched region. So it's similar to what happens at the ionosphere. If you send a light ray which reaches this boundary, then it will bounce back. It cannot enter into this region. And now the question is, how does the shadow look in this case? So it depends very much on where you place the light sources. Let's assume we place light sources here near the inner boundary of this forbidden region and the observer outside of the photon region, but inside the light sources. And then the first thing you calculate is the light rays which asymptotically approach one of these unstable spherical light rays. And this gives you the following shape of the shadow. So if the plasma density is very low, it is constant now, but let's assume it is low, then the shadow looks like that here. If you crank up the plasma density, the shadow becomes deformed, and then it opens out, it forms these fishtails here. So what I show you here is what Alex calls a critical curve. Yeah? So it's what one usually calls a boundary curve of the shadow. It is a set of all light rays, initial directions of light rays, which spiral towards one of these unstable spherical light rays. So there are these funny fishtails, and then yeah, the shadow turns, so to speak, inside out. Yeah. So then if you continue, if you're cranking up the plasma density, now the outer region is dark and the inner region is bright. And yeah, this ends when you reach the value where light rays cannot propagate any longer. So this is if you just calculate mechanically what you are used to from the ordinary formalism. Yeah, the curves which spiral asymptotically towards spherical light rays. But is this really the boundary of the shadow you see? It's not the boundary of the shadow. If the light sources are placed where I told you I want to place them, then actually the shadow turns out to be this here. Yeah, so it's what you see in the sky is not the fishtails. It's actually very similar to the usual shadow, the usual Kerr shadow. So even in a plasma, the shadow wouldn't look very much different from what you, at least in a constant plasma density, what you are used to from the ordinary formalism. So the last part, oh, I'm already over time, sorry. So, but I have 2 more slides, I think. I will go through this quickly. So another thing I want to mention is a bending angle in the Kerr spacetime, with a special case, Schwarzschild spacetime. Actually, for the Schwarzschild case, now I assume that the plasma density is a function of R only. This was first discussed in this paper by Muleman and Johnson in the mid-60s for the weak field approximation. They were interested in light rays which come close to the sun. It was in association with the Shapiro experiment that they wrote this paper, where you considered radio rays grazing the surface of the sun, the solar corona. So there of course, the weak field approximation is very well applicable. The exact formula was given in my book for Schwarzschild, and I also did it for Kerr in the equatorial plane. Yeah, if you have then I assume a plasma density which depends on r and theta, but in order for the equatorial plane to be completely geodesic, you have to assume that this condition is satisfied. Otherwise, the light ray which is sent tangential to the equatorial plane would go away from the equatorial plane. So the bending angle would not be defined, actually. Okay, and here's a formula for the bending angle. So I'm now in the equatorial plane of Kerr. So light ray comes in, goes through a minimum radius, and then goes out again. And what I want to calculate is this angle delta. And here's a formula in the Kerr spacetime. So there's one version of this formula already in my book. Actually, we have a more convenient formula in the first paper with Oleg from 2017. So this is a formula which I give you here. So you have it as an integral over a function f of r, and that's how the function looks like. So it's quite explicit. So you can write down the bending angle quite explicitly. And here's a plot. So that's for vacuum. So there's a bending angle diverges at the photon sphere at r equals 3m, as is very well known. If you have a plasma density, and if the density is high enough, you have a region where the delta phi, the angle which is swept out by the ray, is actually smaller than pi. So the bending angle is negative. So the ray is, so to speak, repelled from the center. Yeah, it's not attracted by the center, it's repelled from the center. And if the plasma density is even higher, this becomes extreme, so the delta phi becomes 0 somewhere. What does this mean? Delta phi equals 0 means the light ray just bounces back. It goes back into the direction from which it came. And that's exactly what happens at the boundary of the ionosphere. Yeah? So this also can happen in a very dense plasma density around a black hole, a Kerr black hole. So, and the last feature I want to mention is that you can have, even on Schwarzschild, you can have light rays, circular light rays off the equatorial plane in a plasma. You have three forces now. You have the gravitational force, you have the centrifugal force, and in a plasma you have a third force, that's the gradient of the plasma density. And these three things can balance each other so that you can have light rays off the equatorial plane. For vacuum light rays in Schwarzschild, this does of course not exist, but in a plasma it can exist. Here's an example. So with this plasma density, it must depend on theta. Yeah, the gradient must have a theta component, otherwise it wouldn't work. So you can have three circular light rays on a sphere, and one of them is in the equatorial plane, and the other two are symmetrically off the equatorial plane. So that's possible in a plasma. As I said, you need to have frequencies which are not very much bigger than the plasma frequency, but they must be bigger than the plasma frequency. In this range, it might be possible to have things like that. Okay, and I have to apologize. I've already run over time. Thank you for listening.